And greetings, everybody. This is Salvador Cordova, and I'm joined by my student James as we begin this first part in a series on college level general chemistry. Now, I've given the lectures earlier. We're going to redo them a little bit since now that I have a student with me that is interested in learning this. Just for what it's worth, this could be a $10,000 course in some colleges here in the United States, which is a lot of money. You could almost buy a used car for that amount of money. But I firmly believe that college should not be that expensive. This course is offered for free, partly because it gives me a chance to learn, or shall I say relearn chemistry. And one of the best ways to learn something or relearn it is to teach it. And so that is my interest in doing this lecture series, is because I need the refresher course so that I could do my job professionally, which is in molecular biophysics. And a big component of anything in biology is the biochemistry aspects. But before there's biochemistry, there has to be organic chemistry studied. And before organic chemistry, there has to be general chemistry. So this is a long road to understanding God's work and being equipped with the tools to appreciate and glorify our Creator for the works that He has made. So before the show began, we actually prayed privately that the Lord would give us enough enthusiasm to make it through. Academics can be very tedious, and just to let you know, even when I was watching some of my own lectures, I fell asleep, even listening to myself, so I can only imagine what this could be like for some of our viewers. But for those who are committed to really seeing the wonder of God's work in biological systems, it is indispensable to, learning chemistry is indispensable to being able to understand God's work at that level. And so, yes, this is tedious, and we're just going to slug through it. And we're just going to read through this text here, which is a free online chemistry, college level chemistry book that's available for free. It's online. You don't even need to download it. They keep updating it. And so the purpose of this is really just kind of to have fellowship as between myself and the viewers and James here, as we just kind of plow through this book. Even though each of us individually could just simply read this book, part of the reason that it's beneficial to have live lectures is the camaraderie, to be able to just go through on this journey and not be alone. James, do you have anything you'd like to say to introduce yourself? In the interest of privacy, just keep everything private that you feel is private. But if you have any words of encouragement to any of our viewers, that would be great.
I don't really have any words of encouragement.
Well, that's actually encouraging.
I think if people watch this show, they are a special kind of person. So I don't really think that kind of person needs encouragement, if you see what I'm saying. We are not preaching on the street, so to speak. We are not throwing pearls before swine.
Amen. Yes, and see, this is also part of, for me, this is part of the Christian walk, is sometimes dealing with the laborious details of life to honor God. And this is going to be one of those situations right here. So with that...
Is this about soap, about bases or something? Or
no, we're going to just... Probably one of the best ways to study chemistry is just study the textbook through and through. It may not... it is certainly not glamorous, and just to update the readers, a college level general chemistry would be like a 1-year course. And then it would
Really?
meet 3 hours a week in lectures. And then for an A student, he should spend an estimated 12 hours in homework and do this for a year. Now, I doubt we're going to be that thorough, but I looked at this textbook and I began to walk through this. I said, this is not going to be a cakewalk. But
I'm sorry.
oh, that's quite all right. This is not going to be a cakewalk. And maybe my role here is just to encourage and say, hey, I'm going to be there to carry this cross. And I don't mean to demean the suffering of Christian brothers and sisters who are really suffering out there in the world, like in Afghanistan.
Yes.
And God bless them. But academics can be a cross to bear, and I say that. I had a cousin, God bless her. She'd come home from school and she was so eager to do her homework. She just loved studying. Scary. She got a PhD from one of America's top schools. That's the sort of temperament that did very well. You know, she had that sort of temperament that would make her do well in academics. Can you imagine someone that is just, she can't wait to get home to start studying more after a day of school? That was her. That was my cousin Libby. I am not like that at all. Okay, so for her, school and homework were not a cross to bear. It was her delight. For me, it was more of a cross to bear. Okay, so this lecture is dedicated to people like me, and James told me in backstage he's kind of in between. So with that, we'll just plow through this and see how it goes. Is that all right with you, James?
Yeah, that's all right.
Okay, and if this doesn't work, this is kind of our experiment. So
Yeah.
For this lecture, I'll probably read through it a little bit.
Let's hope we don't have to falsify this hypothesis.
Okay. All right.
Yes.
Okay, so this is from the OpenStax Chemistry 2E. I'm just going to read straight through, and we'll take a little pause every now and then. Introduction. Figure 1.1. Chemical substances, and I'm just going to expand the screen now. Chemical substances are processes. Chemical substances and processes are essential for our existence, providing sustenance, keeping us clean, healthy, fabricating electronic devices, enabling transportation, and much more. And so there's some pictures of that. And this is the outline. I'm just going to skip reading that. Introduction.
Yeah.
Your alarm goes off, and after hitting snooze once or twice, you pry yourself out of bed. You make a cup of coffee to help you get going, and then you shower, get dressed, eat breakfast, and check your phone for messages. On your way to school, you stop to fill your car's gas tank, almost making you late for the first day of chemistry class. As you find a seat in the classroom, you read the question projected on the screen. Welcome to class. Why should we study chemistry? Do you have an answer? You may be studying chemistry because it fulfills an academic requirement. But if you consider your daily activities, you might find chemistry interesting for other reasons. Most everything you do and encounter during your day involves chemistry. Making coffee, cooking eggs, and toasting bread involve chemistry. The products you use, like soap and shampoo, the fabrics you wear, the electronics that keep you connected to your world, the gasoline that propels your car, all of these and more involve chemical substances and processes. Whether you are aware or not, chemistry is part of your everyday world. In this course, you will learn many of the essential principles underlying the chemistry of modern day life. James, do you have any comments?
No.
Okay, we'll keep going. I'm just going to pause every now and then and just invite that. Oh my goodness, Doki Doki is here. Someone's joining our chemistry class. I have to write Doki a note here and just say greetings. So welcome to our chemistry class. And James, at some point, if you ever want to read, you can. You can grab this, but let's just do this a little bit, and then maybe after a while we can think about if we want.
Yeah, I would say personally that that examples of the importance of chemistry in everyday life, maybe we could skip that because I think it's pretty obvious.
Okay.
I don't know if you agree with that, but
Well,
the other
one of the
parts
problems
are.
is yes. One of the problems is reading in textbooks. You don't know what'll actually be useful,
Oh yeah.
and so sometimes,
But
yeah,
if it's like if they say like, well, we use soap and we use whatever and gasoline and that's all chemistry, right? So I suspect it's something like that, but I'm not sure.
okay. Well, we'll just keep plowing on. We'll keep plowing through this because this is reading a textbook cover to cover is tough because there might be a lot of stuff that we don't need. But you never, if we knew in advance what we actually needed, we wouldn't be reading through the textbook cover to cover. You usually know
that's
what
true.
you need after you've done it. So we'll just plow through this. I'm going to skip part of the outline, the objectives. Throughout human history, people have tried to convert matter into more useful forms. Our Stone Age ancestors chipped pieces of flint into useful tools and carved wood into statues and toys. These endeavors involve changing the shape of a substance without changing the substance itself. But as our knowledge increased, humans began to change the composition of the substances as well. Clay was converted into pottery. Hides were cured to make garments. Copper ores were transformed into copper tools and weapons, and grain was made into bread. Humans began to practice chemistry when they learned to control fire and use it to cook, make pottery, and smelt metals. Subsequently, they began to separate and use specific components of matter. A variety of drugs, such as aloe, myrrh, and opium, were isolated from plants. Dyes, such as indigo and Tyrian purple, were extracted from plant and animal matter. Metals were combined to form alloys. For example, copper and tin were mixed together to make bronze, and more elaborate smelting techniques produced iron. Alkalis Alkalis were extracted from ashes, and soaps were prepared by combining these alkalis with fats. Alcohol was prepared by fermentation and purified by distillation. Attempts to understand the behavior of matter extend back for more than 2,500 years. As early as the 6th century BC, Greek philosophers discussed a system in which water was the basis of all things. You may have heard of the Greek postulate that matter consists of 4 elements: earth, air, fire, and water. Subsequently, an amalgamation of chemical technologies and philosophical speculations was spread from Egypt, China, and the Eastern Mediterranean by alchemists, who endeavored to transform base metals such as lead into noble metals like gold, and to create elixirs to cure disease and extend life. So here is a picture of an alchemist workshop circa 1580.
Yeah.
And yes, go ahead, James.
Oh, what do I have to say?
Oh, nothing. If any of this is, if you just had any comments.
I think it's pretty interesting.
I actually like.
We have to, as Christians, we have to make sure that. Oh, you cut out.
Oh no, I interrupted you actually.
Oh, okay. What I think as Christians we need to be aware that we only use science to observe the world and not to become gods ourselves, so to speak. And that's a mistake that the alchemists made. They wanted to become. They actually made the same mistake that Adam made. in a sense.
I never heard that perspective. One thing, well, we can move on. I will tell you that one reason I like the history when they talk about this is it makes us appreciate what we know now, because when we see the ignorance of where people were and how hard they had to work collectively to discover it, makes me appreciate the knowledge. So
Yeah. But I'm not saying all alchemists did this, but some of them, they did this. They actually wanted to obtain eternal life by creating the Philosopher's Stone, and you can only eternal life is only possible through belief in Jesus Christ. So, I think we see the problem here.
Thank you. Good insight.
But of course, turning lead into gold is another question. That's sort of more of a silly thing, I think.
Yeah. It can be done now, but it's very, very. You have to change the nuclear structure of lead, and it's going to be more expensive to do that than to just simply mine it out of the ground.
Yes.
But I'm just going to go ahead and read this caption here for the picture. So we had the picture of the alchemist's workshop, and then it says B, while the equipment used by Alma Levant Hayden in this 1952 picture might not seem as sleek as you might find in a lab today, her approach was highly methodical and carefully recorded. A department head at the FDA, Hayden is most famous for exposing an aggressively marketed anti-cancer drug as nothing more than an unhelpful solution of common substances. And so that's from the NIH history. Amazing. I'll just continue. From alchemy came the historical progressions that led to modern chemistry. So actually, modern chemistry started with alchemy. From alchemy came historical progressions. Okay, this is really
I'm
fun.
not sure though, because they can claim that, but people have always. I mean, cooking itself is a sort of chemistry. So I'm not really sure we should owe everything to these alchemists, especially if you consider that they had these secret codes.
Yeah. Well,
in which only themselves could, in which they, so.
Oh, that's fine. No,
Hello?
you know what? This is
there?
great.
Oh.
Because I like the fact that just because it's in a textbook doesn't mean that it's true. So great critical thinking. So we'll just keep moving forward. The isolation of drugs from natural sources such as plants and animals. But while many of the substances extracted or processed from those natural sources were critical in the treatment of diseases, many were scarce. For example, progesterone, which is critical to women's health, became available as a medicine in 1935, but its animal sources produced extremely small quantities, limiting its availability and increasing its expense. Likewise, in the 19...
Can I interrupt for 1 second? Okay. Why do you know for which medical use progesterone is used? Because I thought it had to do with menstruation. So do they claim that the so-called pill in which people do not become pregnant anymore, that is some kind of medical application, or are there other applications I'm not aware of?
I'm not aware of. I have on my other computer, I just looked it up, progesterone from Medline Plus. Progesterone is used as a part of hormone replacement therapy in women who have passed menopause. Have not had a hysterectomy. Hormone replacement therapy usually includes estrogen, which is used to treat symptoms of menopause and reduce the risk of developing certain diseases. However, estrogen can also cause abnormal thickening of the lining of the uterus and increase risk of developing uterine cancer. Progesterone helps to prevent this thickening and decrease the risk of developing uterine cancer. Actually, I didn't know that. So I'm glad you stopped.
I didn't either. because I almost thought it was feminist propaganda. I'm sorry for my political.
No. This is
No, no.
good. This. Can I tell you something? You've already livened up the class, because if we're not at all curious about any of this, then it's going to be that much harder. So I'm really glad you asked.
Yeah.
By the way, the other things
but-
that we've harvested from animals are insulin.
But nowadays, they will even claim that killing. Yeah. I'm sorry for the connection. Sometimes it. Yeah. Anyways, what did you say?
We've harvested other things from animals, like before we had synthetic, quote unquote, synthetic insulins.
Yeah.
That we derived by genetic engineering.
Wasn't
we had to get it from
pigs?
Pigs and cows.
Yeah.
Or some mammals. And thank God for that. My mother's life was saved by insulin, by medically developed insulin. So
did she have diabetes?
Yes, she had type 2 diabetes, and yes, mom had type 2 diabetes. I'm just going to pause a little bit here. So she had type 2 diabetes, and I started finding out how they made the insulin that she used to inject, that I injected her with and she injected herself with. That was made by taking human genes and inserting it. They had to reformat the gene and put it inside either yeast or bacteria, and then they would harvest the insulin made by the yeast or bacteria. But before that, they had to extract it from mammals like pigs or cows.
Yeah.
So that's chemistry right there. That's some pretty awesome chemistry right there. But I'll just keep moving. Cortisone came into use to treat arthritis and other disorders and injury, but it took a 36-step process to synthesize. Chemist Percy Lavon Julian turned to a more plentiful source, soybeans. Previously, Julian had developed a lab to isolate soy protein, which was used in firefighting, among other applications. Didn't know that. He focused on using soy sterols, substances mostly used in plant membranes, and was able to quickly produce progesterone and later testosterone and other hormones. Wow. He later developed a process to do the same for cortisone and laid the groundwork for modern drug design. Since soybeans and similar plant sources were extremely plentiful, the drugs soon became widely available, saving many lives. His name is Percy Lavon Julian.
Okay. I will look.
I'm glad you're interested.
That's pretty interesting.
Yeah, making testosterone from soybeans.
Oh, is he one of the? Wasn't he one of those people who worked in the? He was a black scientist, if I understand correctly, one of the first. So that's pretty interesting.
Yes, indeed. You're very astute.
His father James. So his grandfather was actually a slave, and so do you see the progression in 2 generations? That's incredible.
That is. What a great role model for everyone. Amazing.
Yes. Another one is Thomas Sowell. I think he grew up in a ghetto, or wasn't it? Or was it the Black Republican? The neurosurgeon. I forget his name.
Ben Carson. He was actually
wasn't
supposed to speak at my graduation in 2013.
Really?
Yeah, but he had to back out because he said marriage is between a man and a woman, and there were protests over him saying that.
Was really, this at Johns Hopkins?
Yeah, Johns Hopkins.
Yeah.
He was a surgeon at famous neurosurgeon at Johns Hopkins. He was going to give the graduation address, but because of his Christian beliefs, he said marriage is between a man and a woman. There were protests saying they don't want him as graduation speaker. So I was kind of upset because I really wanted I wanted Ben Carson to speak at my graduation. There was a very fine surgeon who spoke instead, Hinojosa, who is also a great story. Oh, go on. You had a
Oh yeah, yeah. I think it's sad, but I wanted to say, no, I like Ben Carson. So
yes. So we'll continue. See, this is good. We need a little bit of break during lecture. Keep it interesting.
yeah,
Chemistry is sometimes referred to as the central science. Chemistry is sometimes referred to as the central science. And I want to say it's not evolutionary theory. The central science is chemistry.
yeah.
We can do science without evolutionary theory.
Oh, but didn't you know that abiogenesis is scientific fact? It has been proven many times. we can replicate the experiments effect.
Yeah. But we'll continue. We're going to have too much fun. So chemistry
Yeah,
is
I'm sorry.
sometimes referred to as the central science due to its interconnectedness with a vast array of other STEM disciplines. STEM stands for areas of study in the science, technology, engineering, and math fields. Chemistry and the language of chemists play vital roles in biology, medicine, materials science, forensics, environmental science, and many other fields. The basic principles of physics are essential for understanding many aspects of chemistry, and there is extensive overlap between many sub-disciplines within the two fields, such as chemical physics and nuclear chemistry. Mathematics, computer science, and information theory provide important tools to help us calculate, interpret, describe, and generally make sense of the chemical world. Biology and chemistry converge in biochemistry, which is crucial to understanding the many complex factors and processes that keep living organisms, such as us, alive. Chemical engineering, material science, and nanotechnology combine chemical principles and empirical findings to produce useful substances ranging from gasoline to fabrics to electronics. Agriculture, food science, veterinary science, and brewing and winemaking help provide sustenance in the form of food and drink to the world's population. Medicine, pharmacology, biotechnology, and botany identify and produce substances that help keep us healthy. Environmental science, geology, oceanography, and atmospheric science incorporate many chemical ideas to help us better understand and protect our physical world. Chemical ideas are used to help understand the universe in astronomy and cosmology. So that's actually a beautiful diagram right here
Yeah.
that shows chemistry is the heart of so many of these. Me having studied physics,
Yeah.
people
It's
will.
sort of subjective.
Yeah.
I would say that mathematics is more fundamental, or even philosophy, or religion. Christianity.
Well, each person has their viewpoint.
Yeah.
I
Do you
would
know
actually-
about Cornelius Van Til?
Yes, he's a famous Christian apologist, and actually,
Yeah.
I've actually never liked his work. I'm sorry to offend you or anyone else.
Oh, really?
Yeah.
I'm sorry. I'm a presuppositionalist. So.
Well, it's very.
Okay.
I'm an
Let's
evidentialist.
agree to disagree.
I'm sorry.
Let's agree to disagree. It's not an.
So, what the nice thing is, I just want to point this out briefly, that when working professionally with John Sanford, he sent me off to learn about God's creation to secular schools. So that meant I was learning about God's work from atheists, or at least evolutionists. They may be, I don't know what their religion was. They could have been theistic evolutionists. I don't know. And actually, I know one young Earth creationist, brilliant, but she has to teach evolutionary classes because she works in a secular. I don't know how she's able to do it. I couldn't, I would have a hard time.
Well, I know the theories. I could explain the theories very well, actually, but I just don't believe them. I think that's the reason I don't believe them, because I understand them.
That's true. So all this to point out, there are some aspects of science that are independent of what one's religious basis is.
Yeah.
That, I
But
can
I
read
would
some.
say, yeah.
Yeah. Go ahead.
Oh yeah, I'm sorry. I would say that God is without God you cannot have logic, and logic is the fundamental of science. So that would be, or mathematics, and then you have science. So that would be my reasoning.
Well, I fundamentally believe.
I would say that God precedes logic. That's my opinion.
I would say that the world would not exist without God. Nothing would.
Yeah.
Whether man accepts that or not, we can still do science. Meaning, someone
Yeah.
can reject God.
You can deny gravity, but if you jump off a skyscraper, you're gonna die.
Right.
So, yeah.
But all this to say, when Dr. Sanford sent me to biology school, he knew that I'd be learning from people that had a different worldview, but I could still, there were things that they could teach me that I could learn without necessarily having their worldview. So
didn't Paul say that in 2 Corinthians something, or 1 Corinthians? I forget. I'm not.
Yeah, that's interesting.
Really good
Well,
memorizing.
we'll just move on. We can
research everything.
We can have these
yeah.
philosophical conversations in philosophy class.
Oh, I'm sorry. I'm very sorry.
It's okay. No, this keeps it interesting, because otherwise we'd be putting each other to sleep. So it's good. This keeps this session.
I will shut up now.
No, I've invited you to talk. That's
yeah,
otherwise
okay.
I'd just be doing this lecture like I did before. So what it says here, knowledge of chemistry is central to understanding a wide range of scientific disciplines. This diagram shows just some of the interrelationships between chemistry and the other fields. I'd actually tend to lean, I'd put mathematics at the center, then physics, and then chemistry. Because I think physics underlies math, and physics underlie everything else. But that's not really important to learn in chemistry. But what are some changes in matter that are essential to daily life? Digesting and assimilating food, synthesizing polymers that are used to make clothing, containers, cookware, and credit cards, and refining crude oil into gasoline and other products are just a few examples. As you proceed through this course, you will discover many different examples of changes in the composition and structure of matter, how to classify these changes and how they occurred, their causes, the changes in energy that accompany them, and the principles and laws involved. As you learn about these things, you'll be learning chemistry, the study of the composition, properties, and interactions of matter. Actually, this is interesting. People have asked me to define what mathematics is, or physics is, or electrical engineering, or information theory, or what information, and then what chemistry is. So this is actually a definition. It's the study of the composition, properties, and interactions of matter. That's one definition. It's probably not the only one. The practice of chemistry is not limited to chemistry books or laboratories. It happens whenever someone is involved in changes in matter or in conditions that may lead to such changes. Scientific method. Chemistry is a science based on observation and experiment, unlike evolutionary theory. Doing chemistry involves attempting to answer questions and explain observations in terms of the laws and theories of chemistry, using procedures that are accepted by the scientific community. There is no single route to answering questions or explaining an observation, but there is an aspect common to every approach. Each uses knowledge based on experiments that can be reproduced to verify the results. Some routes involve a hypothesis, a tentative explanation of observations that act as a guide for gathering and checking information. A hypothesis is tested by experimentation, calculation, or comparison with experiments of others, and then refined as needed. And I can say that is not at all what evolutionary theory is or evolutionary biology. If you have any thoughts on that, you're welcome to offer them right now.
Well, with regards to the scientific method, people often forget that it's a method. It's not a overarching worldview. And so sometimes people will worship science and they act like it's some kind of religion. Like you have science and you have councils and people deciding dogmas. But that's not what science is. It's just a method. That's at least that's my opinion on it.
Oh, great. So let's move on.
Do you agree or not?
I actually never thought about it that hard. Where I'm at with this is evolutionary theory follows none of that. None of that.
Yeah, I agree.
With experiments and observations. They've never observed eukaryotic evolution, but they'll assert it. They can't repeat it. And everything we know about cell biology doesn't agree with it. So it's like, well, how can you assert that this happens naturally? And what I mean by natural is that would we expect something of this magnitude to eventually happen? At what point does this violate everything we know about statistics and cell biology?
I really think it's only to justify a silly lifestyle.
Yeah. It's probably more nuanced than that, but that's subject of another lecture. Anyway, some hypotheses or attempts to explain the behavior.
I'm sorry.
No. I'm the one who threw it on the table because this is important. This makes the class fun. Otherwise, we'd be both going to sleep. And I think I almost fell asleep giving one of my own lectures in addition to listening to them. So some hypotheses or attempts to explain the behavior that is summarized in laws. The laws of science summarize a vast number of experimental observations and describe or predict some facet of the natural world, such as a hypothesis turns out to be capable of explaining a large body of experimental data. It can reach the status of a theory. Scientific theories are well-substantiated, comprehensive, testable explanations of particular aspects of nature. So scientific theories are well-substantiated, comprehensive, testable explanations of particular aspects of nature. Theories are accepted because they provide satisfactory explanations, but they can be modified if new data become available.
I'm sorry for interrupting you, but atheists, they will always memorize this definition. And then if you say, well, I don't believe in evolution, it's just a theory or something, they will always throw this at you.
Well, the thing is, evolutionary theory is not well substantiated. I'll tell you exactly why. Okay, so there are two theories. There's abiogenesis theory. Could absolutely say that's not well substantiated. I mean, anyone who's listened to James Tour's lecture. Oh, by the way, did you watch James Tour's lectures?
I haven't yet because I'm more into theology at the moment, but I will certainly do it when I'm back into. This is my return into science land, so to speak.
Oh well, then I'm glad you're coming here.
Yeah.
He brutalized the state of abiogenesis. He is calling them out, saying that's false. These guys are lying. And he demonstrated it with chemistry, and he's one of the best chemists on the planet. So that was really awesome just to hear him rip into it. And so abiogenesis is not well established, substantiated. Same for eukaryotic evolution. Absolutely not well substantiated, but they still believe it.
Wasn't there some professor at the University of Missouri you talked to?
Oh yeah, she's still there, barely. They are getting after her. James here is referring to Dr. Change Loratan. She's been on one of my other channels talking about molecular biology, and she is criticized. She teaches about eukaryotes and prokaryotes, and in her class, that's part of her job. Outside of class, she points out why one cannot evolve from the other, just from everything we know. So I don't know how people could say I'm a science denier because I deny evolutionary theory. I wanted to say evolutionary theory is denying. It's something that's the science denying theory, to say that these things can naturally happen.
Yes.
So, I mean, some parts of the theory can naturally happen. For example, there's certain genes that humans share with chimpanzees that are 100% identical. So,
Yes.
in a sense, yes, if we evolved from an ape-like ancestor, specifically those genes don't need a miracle. It's the other parts that do. So,
Yes. It's
subject
also
of
funny
another.
because they will always make fun of us for believing that the creator of the universe walked on water. I mean, he created water, so why shouldn't he be able to walk on it? Anyways, and they make fun of us for believing that. At the same time, they believe in all kinds of weird miracles.
Yes, absolutely. Eukaryotic evolution is one of them. So this is great. We've helped make this lecture more interesting, because otherwise we'd be going to some of us. But wait till you get to some of the harder aspects of chemistry.
Well, I actually like calculating, so I hope it will be more mathematical.
Yes, yes. Okay, so theories are accepted because they provide satisfactory explanations, but they can be modified if new data becomes available. The path of discovery that leads from question and observation to law or hypothesis to theory, combined with experimental verification of the hypothesis and any necessary modification of the theory, is called the scientific method. So we talked about the method. So we have here this diagram. So it begins with observation and curiosity. We form a hypothesis, make a prediction. We perform an experiment, and we see if the results are consistent with prediction, and we make new hypotheses. And it contributes to the body of knowledge. Further testing, if it doesn't support the hypotheses, we start from scratch. And then we get much additional testing yields constant observations, becomes a law. And otherwise it becomes a hypothesis. Hypothesis becomes a theory. So we can have laws and theories. So in physics, we do have things we will call laws, like the second law of thermodynamics, or the first law of thermodynamics, or the zeroth law, or the law of conservation of energy. Let me see. Then we have things we'll call principles in physics, like the principle of least action. And there are other, some things would be just described as equations, but they're very close to what we would call a law. We may call electromagnetism a theory, but
yes.
In practice, it's a law. It's like, okay, you can't, it works so well that you would expect it, we call it law-like.
Don't you have the Maxwell equations or something?
Maxwell's equations, exactly.
You had two equations, I thought.
And which other one?
Weren't there two sets of equations? I forget the other name. You have one which
there are five
major.
There are five major pillars of physics. It would be Hamilton's equation, Hamiltonian classical mechanics, which would include Newtonian mechanics. So that's one.
Who is Hamilton?
Sir William Rowan Hamilton. He codified classical mechanics, which is Newtonian, but he made it more. He added much more mathematical machinery to.
Oh, I know him. Isn't he the guy who invented? Yeah. Anyways, I'm sorry for interrupting.
So we have Hamilton mechanics, and then next would be another one would be electrodynamics, which is Maxwell's equations. The third would be statistical mechanics, which is Boltzmann's equations. Then next would be quantum mechanics, which is represented by Schrodinger's equation and Heisenberg uncertainty. But those equations are not the complete theory. So those who really understand quantum mechanics know that's much larger body of knowledge. And then finally, relativity, or relative, what I call sometimes relativistic mechanics. And those are that will cover a very large amount of physics. one could have several lifetimes just to study those 5 pillars. Their physics is more than that, but I'd say those are the foundations. So going back to this diagram here where we're talking about laws, theories in physics come very close. Many of them we would describe as laws. Now, I wanted to say, I almost laughed. I said, okay, how does evolutionary theory fit this diagram? So when the hypothesis fails, one, they don't really make any predictions that we can actually test in the current day. And when it's criticized, it's like, well, then you suppress criticism. You don't actually redo your theory. I know I'm saying really mean things, but I just had to say, coming from a background where I studied physics and engineering, I just like evolutionary theory that only pretends to follow this diagram here. When it's subject to scrutiny, and we can also say the same of abiogenesis theory, we see that it is actually to reach the level of theory where it says hypothesis becomes a theory. It's followed really none of these steps. So that's not really being truthful when they advertise it as being a great theory. It's absolutely not. It would at best be just at this stage here where it says form a hypothesis, not even make a real prediction.
Yes.
Form a hypothesis. That's about it. So that's about the only part that it fulfills. It doesn't qualify to become up here. And
that would predict
speciation,
wouldn't it? Would predict I would speciation, say, which we would discover 5 million years from now.
I'd make a very simple one. I said, tell me your theory of eukaryotic evolution. Yeah. How does that square with any experimental evidence? And yes. I mean, that's where I go. So anyway, the scientific methods follows a process.
But isn't it funny that if they're for that?
Go on.
Yeah, I'm sorry. I think the connection is sort of lagging sometimes. So I'm talking and I can't hear you. So I think you are silent, but then you're talking, and vice versa. I think so.
We are a little slow. That happens. So Go ahead. You had something on your mind?
Yeah. I think it's funny that their predictions to be confirmed would take us probably millions of years before we could confirm their prediction, which is of course ridiculous.
Yes. And the reason, just briefly, the reason we know it would be ridiculous is we have better understanding of genetics, chemistry, cell biology, and we can then put it in equations and say this is not going to happen. If someone wants to challenge me on that, I've debated this topic, eukaryotic evolution. There are aspects of evolution that would work, but there are many more parts that would not. So what do you do?
Yes.
Anything that's a deal breaker, it's over. It's just like a password. If you miss one character, it's just not going to work. 90%. You getting 90% of the characters right is not going to be sufficient. So there could be deal breakers.
Yes. Personally, I got convinced that evolution is totally ridiculous when I read Genetic Entropy by John Sanford. It totally dismantled the last vestiges of belief in evolution in me.
Wow. For me, it was studying eukaryotic evolution with Dr. Tan. So I had already studied genetic entropy, but when I read Dr. Tan's work on eukaryotic evolution, I said that no way. People have debated genetic entropy on the net. No one will debate.
Could you send that to me?
Oh yeah. Hang on. Let's do a quick timeout because there's a request to send this. I am going to see if I can bring this up. information processing, eukarya. Now, I wish she didn't publish this in Answers in Genesis. This was good enough to publish anywhere, because this is written by a scholar, and she was picked by a Nobel Prize winner to teach molecular biology. So she's very good. I'm going to dump this. Oh, One Calp Stampede is here. Oh my goodness, we got an audience. See, I'm glad we're doing this. This is changed hands eukaryotic critique. Oh, 6-exotrig is here. Fabulous. Okay, so we're gonna just keep flying through this chapter. We're halfway through this section. The domains of chemistry. Chemists study and describe behavior of matter and energy in 3 different domains: macroscopic, microscopic, and symbolic. These domains provide different ways of considering and describing chemical behavior. Macro is a Greek word that means large. The macroscopic domain is familiar to us. It is the realm of everyday things that are large enough to be sensed directly by human sight or touch. Okay, that's kind of a qualitative definition of macroscopic. In daily life, this includes the food you eat and the breeze you feel on your face. The macroscopic domain includes everyday and laboratory chemistry, where we observe and measure physical and chemical properties such as density, solubility, and flammability. Micro comes from the Greek and means small. The microscopic domain of chemistry is often visited in the imagination. Some aspects of the microscopic domain are visible through standard optical microscopes. For example, many biological cells. More sophisticated instruments are capable of imaging even smaller entities such as molecules and atoms. However, most of the subjects in the microscopic domain of chemistry are too small to be seen even with the most advanced microscopes, and may only be pictured in the mind. Other components of the microscopic domain include ions and electrons, protons and neutrons, chemical bonds, each of which is far too small to see. The symbolic domain contains the specialized language used to represent components of the macroscopic and microscopic domains. Chemical symbols, such as those used in the periodic table, chemical formulas, and chemical equations, are part of the symbolic domain, as are graphs, drawings, and calculations. These symbols play an important role in chemistry because they help interpret the behavior of the macroscopic domain in terms of the components of the microscopic domain. One of the challenges for students learning chemistry is recognizing that the same symbols can represent different things in the macroscopic and microscopic domains. And one of the features that makes chemistry fascinating is the use of a domain that must be imagined to explain the domain that can be observed. I think that's really profound. One of the features that makes chemistry fascinating is the use of a domain that must be imagined to explain behavior in a domain that can be observed. So let me say, if you have any thoughts, James, and I might try to, while you're talking, I'll try to think of an example of that.
You mean the difference between symbolic and macroscopic, etc.? Or
okay, so I'll give an example that there was.
I do have a microscope, so.
Well, I'm trying to think. There was a case where Linus Pauling, he was a Nobel Prize winning chemist twice. and he was imagining how water molecules would connect to each other. This is what they call a famous case of what they call configurational entropy. And he was able to then calculate the changes in temperature. If you pump heat into ice, this is what you would expect. This is how much heat you might need. So he is using his imagination to describe. And then there are people that were thinking about, so there are a lot of chemical structures that we imagine how they connect, and we can say, okay, this is very strong or very weak, and we can kind of estimate how it's going to behave. Like, say, the diamond. A diamond, we have a conception of how the carbon atoms are connected, and it's a very strong way that they bond, and it explains the properties of why diamonds are so hard. So those are off the top of my head. There are probably others. I think, like, I know that in like the development of glass or electronic devices, they imagine how the atoms are and molecules are interacting to be able to give it its properties. So like how we make a transistor, we have these fascinating ideas of how the molecules are together, and it creates what one can describe it as the movement of virtual particles inside the transistor, what we call electron holes. So we're actually imagining how this works. So it says chemistry, one of the features that makes chemistry fascinating is the use of a domain that must be imagined. So many times we can't see things, we have to imagine it in order to explain the behavior of what can be observed. So the Nobel Prize winner was granted to Shockley, who made the first transistor. And for a long time,
Yes.
and even to this day, we have to still imagine how things happen at the molecular and atomic level to explain how the transistor behaves. So we actually do have to use imagination at some point to try to have insight into how this works, because we can't actually directly see it. And so this does have spiritual principles, obviously, when you have to accept something that you can't actually see to explain what you observe. So for creationists, we believe in the invisible God who we can't see, and he's the explanation of what we observe. To me, he's the best explanation. That's why I'm a Christian. That's one of the reasons I'm a Christian. I believe God is the best explanation. It says in Romans, his divine nature and eternal power are clearly seen in the things that are made. His invisible attributes, namely his divine power, his eternal power and divine nature are clearly seen in the things that are made. Oh, 6esoteric says, in chemistry, we often imagine transition states to explain reaction mechanisms. There you go. Obviously, this looks like a resident chemist weighing in here. So we're almost done with this section, and maybe we'll call it a day. It's not going to be, the rest of the lectures are not going to be as nice as this, but this is a good start. A helpful way to understand the three domains is via the essential and ubiquitous substance of water. That water is a liquid at moderate temperatures. Will freeze to form a solid at lower temperatures and boil to form a gas at higher temperatures are macroscopic observations. Some properties of water fall into the microscopic domain, what cannot be observed with the naked eye. The description of water as comprising 2 hydrogen atoms and 1 oxygen atom, and the explanation of freezing and boiling in terms of attraction between these molecules, is within the microscopic arena. The formula H2O, which can describe water at either the macroscopic or microscopic levels, is an example of the symbolic domain. The abbreviations G for gas, S for solid, and L for liquid are also symbolic. And so this is actually a nice picture here. So we see the macroscopic domain, and if you could see it here, like the clouds, it puts H2O with a G, so there's water in the air. And we can symbolize it with H2O and a G for gas. And then we have water in the solid state here, and we represent it as H2O with an S. And then we have water in the
I don't see a picture.
You don't? Oh, apologies. Here we go. Thanks. Sorry. Do you see it now?
Yes, I can see it.
So I apologies to the viewers. I didn't realize I didn't have the picture there. So we have H2O. This is how we can symbolically represent gas in the gaseous state, the vapor state of water with H2O. And there's a picture of it here, really the clouds also. And then we have solid water, H2O with an S, and that's macroscopically, it is this big ice or glacier, but we can represent it symbolically as H2OS. And then we have water in its liquid state, H2OL. I don't think that's particularly difficult, but that's one way to see how we have kind of the symbolic realm of chemistry, and then the macroscopic.
And the distance between the molecules is important, of course.
Yes, you can see it's much here in the gaseous state, they are far apart. In the liquid state, they're close enough. And I believe what causes them to form the liquid state are what they call hydrogen bonds that break and connect. And then in the solid state, you have, I guess it's crystallizing here of some sort. It goes into this, it's a different arrangement of the water molecules. So in the gaseous state, that's very simple. They're just bouncing around because they have a lot of velocity, or kinetic energy is the more proper term, has a lot of kinetic energy, and they can't stay together. When the kinetic energy is reduced, it'll go into liquid state, and when it's really reduced, they'll even connect and form solids. So we're able to conceptualize this crystal structure, this solid structure. I think we can actually see it now, maybe with our instruments of X-ray crystallography. We can confirm that this is how it connects. So anyway, I'll just keep moving. We're almost done for today. So I'll just read this. Moisture in the air, icebergs, and the ocean represent water in the macroscopic domain. At the molecular level, microscopic domain, gas molecules are far apart and disorganized. Solid water molecules are close together and organized, and liquid molecules are close together and disorganized. The formula H2O symbolizes water, and G, S, and L symbolize its phases. We call them phases. So we'll use that word. We'll study that some more. Note that clouds are actually comprised of either very small liquid water droplets or solid water crystals. Gaseous water in our atmosphere is not visible to the naked eye, although it may be sensed as humidity. And let me just see what's next. So that's it for today. Do you have any comments on our introduction to chemistry or reflections? And then we could talk about maybe next time what we'll do.
I don't really have anything to say.
Well, I think this was fun. I'd like to thank all of our viewers. And this was this is an experiment in kind of conducting the lectures in a more less formal way. We're trying to make this fun because academics can be tedious and challenging, and this is kind of my way of trying to make it more accessible. So with that, I'd like to thank all of our viewers. It's been great to see Doki, 1 Cow Stampede, and 6 Exo Trig. And James, it's great. And so I don't know quite what our schedule will be, but we'll just kind of, I hope we'll do this again. So with that, I'm going to shut the stream down. Take care, everyone, and God bless you. Have a